presentation we will cover the static timing analysis. There is a tool available with the development kit that it's called the SPU timing tool. So it will give, once you write your code, you want to see how many stalls were there, how many branch operations were taken, where were the delays, where were the dependencies. So this is a static analysis tool which will parse your code, look at the assembly file and see and basically try to give you an analysis of how the code is interleaved. So basically this is how it's done. Take a simple source code, example.c, produce the assembly file and then produce the annotated assembly source, like it will in your current working directory. When you run the command with the timing tool, there will be a file .s.timing. If it's an example.c, there will be an example.s.timing tool in the current working directory. And this is the command options. You can this is how you say SPU underscore timing, and these are the options that you can give on the command line. Help will display whatever the verbose thing, and then you can specify the architecture. Are you trying to profile basically you can provide the target architecture with the -m option, and then you give the name. If you don't want the default naming, you can give a different kind of name on the command line. And then you can count the number of cycles from the start of each instruction by giving this parameter -running-count, and then the input file. So now let's look at a source file and see how basically this tool is used. In input vector, there's an input number n coming in, one float variable coming in. There's an array of vector. There's an array of vec underscore float, and then there's another array y, x and y. So SPU underscore splats takes an input value of a scalar variable and then produces a vector variable. So what this vector element A will have, now alpha is what, a float variable, right? So this vector A, it's a vector. So there will be 4 floating point variables in that vector A. So SPU underscore splats will take the scalar value alpha, may say it is 4.5. Right? It will inside the vector A, it will put 4.5, 4.5, 4.5 and then 4.5. So there will be 4 values of replicated across the whole vector. And then you do a multiply add. It's basically multiply x, I and yi, and then you add it to A. So this is what this simple scalar code is doing. Once the assembly code is produced, this is how a typical assembly file looks like, right, for any source code, a simple C program. Now, this is the annotated source, example.s.timing. That was the example.c, and this is the annotated source code. Now, let's look at the different features, how to basically understand what this source code, this timing file is saying. So, the first thing to observe is the running count. Over here, there are basically a few important columns, right? This is the first column to observe. This is the second column to observe. Again, we will go into further details of what these columns mean. And then there is a third column over here, which gives you the pipeline, an idea of how the instruction pipeline is looking like. And then the text portion and the data portions over here, and the instructions and everything. Okay, so the running count, right? The cycle count for, basically running count is a cycle count for each instruction. Every time an instruction starts, it tells you how many cycles is that instruction taking. So in other words, if it is a shuffle B operation, it takes 2 cycles. So by adding up all these values, right, for our example, our loop is 17 cycles, right? Because so this is where our loop is starting, right? So 23 and then 6, 23 to 6. So this is how you analyze how many cycles it takes. And this is again a static analysis tool. There is more tools available which make it a little more simpler, give a little more simpler output. This is the execution pipeline. We always keep talking about dual issue, right? How do we make sure that there is actually dual issue happening? So in this one, every time there is a 0 or 1, the first column in this, or the first sub column in the second column always tells you which pipeline it's going into. So if it's a 0, it's the even pipeline, right? If it's a 1, if it's a 1 over here, it's the odd pipeline that this particular instruction serially is using. dash D, there, if you notice there is some D's are capital letters and there is some D's that are small letters. So the second sub column in the second column talks about basically the dual issue status. Is the dual issue actually happening or is there a dependency? So if there is a small d, basically it is saying dual issue is possible, but there is some dependency. So that instruction can be issued along with the even pipeline or the odd pipeline, but there is some dependency that's stopping that's stopping the issue of dual instruction, that will stop the dual issue at runtime. And if it's a capital D, it indicates that yes, it will be dual issued. So in other words, it's a good thing when you see 0 capital D and a 1 capital D. That directly means that yes, capital D dual issue is possible and it will happen. And a 0 and 1 means what? It's a even and odd pipeline. So ideally, your second column should always look like 0D, 1D, 0D, 1D, things like that. That means your code is really efficient. Otherwise, you have to see, oh, there is some dependencies now and try to rearrange, restructure the code so the dependencies is removed. Now let's look at the third column. This is the pipeline. Instruction clock cycle, which denotes the instruction clock cycle occupancy. So there's different digits if you see. A digit 0 through 9, basically it will, it is for every instruction clock cycle there is a digit that will be displayed. And if there is a dash, you can always accept, basically that means there is a dependency. The instruction is ready to be issued, but it cannot be because there is some dependency with the previous instruction. So there is a stall basically. Therefore, if there is a steep sloping of this instructions digits, that's actually very good, because that means less dependency and it means efficient issue of instructions. And shallow sloping, usually I think even this is probably okay, but it could be better. I mean, if it goes like that, like the slope, it's very good for your program. If it's like this, shallow is not good because it just denotes that there's more stalls. Now let's see the inner loop. Over here, for example, we're seeing that these two portions are showing a lot of dependency stalls, right? So basically the load of Y stalls one cycle for address increment if there is one dash. So therefore the store of the resulting Y, right, stalls 5 cycles if there is 5 dashes waiting for the FMA operation, this operation to complete. I think they're looking at over here. So for the FMA operation to complete, there's 5 cycle stalls over here. So let's see what else. Now dependency stalls can be eliminated by unrolling the loop. However, let's keep one thing in mind. Even when we are unrolling a loop, make sure that you're not using local variables that are not the same. For example, if there is a variable A that needs to be computed in the first unrolling of the loop, use different variable names. Otherwise, if it's the same variable, the compiler gets confused and it thinks, oh, for the second version of unroll loop, I need that variable. It's not needed, but it introduces false dependencies. So even though you give the optimization O3 level to the XLC compiler, nothing might happen until you make sure that these false dependencies are not introduced in the code. Okay, profile markers. There is something called, there is a header file profile.h which has instructions which read prof_cp and then there is a number. It could be 0 through 1 or pick any numbers that are consecutive. You can say prof_cp0 and then prof_cp1 and keep the loop in the middle. Let's look at an example before we talk any further. So for example, this is our loop, right? This is our vectorized code. So now we want to see what is the performance number. Now we don't want to basically capture all this overhead. We want to capture any time we want to profile code, it should only be in front of the computation, just before the main computation kernel starts and then after it ends. So in this code, when do we want to start profiling? Right before the loop, and we want to stop profiling right after the loop. So if you see, the for loop is starting right here. We start prof_cp0. What it does is it starts capturing the cycle information. So it will start capturing the information for all the loop iterations, and then it will print number of cycles it used up, number of stalls, and it will produce all this information in the timing tool and the statistics on the simulator. And in the assembly code, you can identify it because it introduces this instruction over here, the L no op instruction. Okay, let's see, there are some limitations. If you are writing your handwritten assembly code, it may not work as well. This is a language that the compiler understands because it is trying to do the disassembly of the code. It is trying to just generate the assembly, so it understands its own effort. It's like someone else cannot understand your code, something like that. So if it's handwritten assembly, running the timing tool on handwritten assembly may not produce the same results. It's always, the most beneficial use of it is when you're writing the source code in a high level language, C, C++, whatever, and then you're trying to profile it via the you're running the timing tool on it, because the compiler itself is generating the assembly file. So that's the static timing. Let's go over to the dynamic runtime analysis. How do we do that? So the class objectives for this is to see how to do runtime dynamic analysis and how to produce that output on the simulator in a very user-friendly, understandable manner. Alright, so when we do these profile checkpoints that we covered in the previous presentation, this is how you can introduce profile checkpoints: prof underscore clear, prof underscore start, and prof underscore stop. Now when you do that, it will produce an output of number of cycles consumed, and here is your loop part. This is something that you will introduce in your code. This is the output that it will generate on the simulator. It will say, depending upon the number of the SPU used, it will print the SPU number over here, and then it will say CP31, that's a checkpoint. And then it will tell you the instruction counter, total number of instructions, including the no-op and the outer braces, and then in the braces excluding no-ops, and then the total number of cycles used. So for these many instructions, the total number of cycles used were these many. And in order to extract that kind of information, we need to tell the simulator that you cannot just run in fast mode. We have to change the mode of the simulator to say pipeline mode. So in other words, when you put the simulator in the pipeline mode, it will record every single cycle. These are the instruction classes. All the instructions that we are dealing with, arithmetic, memory, all these instructions fall under a certain category. And that category is defined, and the even and odd pipeline is based on that category. So all single precision floating point operations are called FP6, and they're always in the even pipeline, right? All the branch instructions, because it's a kind of, it deals with memory, so will be falling under BR class, and it will go to the odd pipeline. The no-op, loads and stores, branch and branch hence all fall under this category, LS and L no-op. And then there's the loads and stores can be, they take 6 cycles every load and store, and then they go to the odd pipeline. And all this information is necessary when you're basically writing your simple application. And because if you're trying to do an add, right, you will know that it will definitely go to the even pipeline because it's an arithmetic operation. So after that, if there's an if-else statement, you want to structure your code so that if there is a branch taken, make sure that it is right after the computation or right before it. So the compiler can automatically restructure the code and issue it in the 2 pipelines. So it's concurrent. The point of you making it, forcing the dual issue or writing the code so that the dual issue happens is so that you save the cycles, right? It's all about the cycles. We're going to reduce the cycles at any cost. Bottom line. Okay, so there is the simulator provides these statistics. You can basically type on your command prompt like this particular command, and it will print some data. We will see that in the hands-on session. If you want to use the GUI controls, so in other words, you run your application. Yesterday you run hello_be, right? You run your hello_be, and then you go over to your SPU, and you do this command SPU stats, and it will print this whole window, provided the simulator is set in the pipeline mode. Now the simulator output will be looking like this. So the first section gives you the complete summary. It tells you the total number of cycle count, the instruction count, and CPI. So number of cycles per instruction in the code. So it's a very useful thing because a lot of times, actually, before I joined cell programming, the most I used to think about is how to write object-oriented code and how to make sure that it's the coding standards are good. And but I never really worried about performance until I started working on the cell programming, and then there's a few things that I realized I could just do real neat, and I could apply it back if I went back to my previous position. But it's really neat to write the code and see exactly that, oh God, I suck at this, it's terrible. And then you go back and you improve your code and you restructure, do things that just make it so much more efficient. So it gives, in other words, if your cycle count is way too much and you know that it's a small code, obviously there's something wrong going on. And it's not visible to the naked eye, but you have all these tools to run on the code to basically observe the behavior and improve it. Okay, so this is the full summary of the output, right? Now let's go deeper down. The first section gives the total number of cycles and the instructions, complete instructions executed by a program, and then the cycle count. Usually it should be somewhere less than 1. It's really good if it's less than 1. Usually it should be between 1 and 2, because otherwise there's something not right if there's more than 2 or 3 or 4. So total number of cycle count is here, instruction count is here, CPI is here, and then let's say the performance cycle count. Basically the performance cycle count is basically when you started profiling the code, right? Before the total cycle count is all the instructions for the entire code. Performance cycle count is for the parts that you're trying to profile and optimize that particular kernel. And then you can also get performance no-op count, and you can also get performance instruction count. You can also get branch and hint statistics. So you have all these. The total number of branch instructions is 14,000 something over here, right? 143,000. So you have taken these many branches. No wonder the cycle count over here is so high, 8.55. Branches not taken is 280. So you can get all these statistics that determine the nature of your code. And if you have used any hints in your code, it will give you a summary of how many hints actually worked. There's also this efficiency statistics, single cycle, number of dual cycles, how many instructions did use the dual issue pipelines. There's also no-op cycles. It's a really neat summary of everything that you can possibly know about your code. Prefetch miss, dependency stalls. If there's any dependency stalls, it will give you a complete list of how many dependency stalls were there. So in other words, the point to notice over here is dual issue cycles. So the point to observe here is basically to see how many dual issue cycles were there, how many prefetch miss stalls were there. The most important thing, the dependency stalls. Reduce dependency, reduce dependency, reduce dependency in the code. That's the key, because otherwise no matter how good the code is, you're trying to vectorize it, if there's dependencies, it cannot be parallelized. The compiler has got immense capability to parallelize your application, but if it's not well written, even the compiler cannot do anything unless you want to write your own assembly code. Alright, what else? Hint target stall, pipe hazard stall, all this information. This can be very useful presentation for you to refer back to when you're when you go back from this class and you write your own application code. Refer to these features available and see what they mean and how to use them. Okay, and then there's another command line option available which says on the command simulator prompt, once the simulator is running, that window which gave all this garbage, all this addresses and all this trace output was coming over there. You can go to that window and hit Ctrl+C, it will give you the command prompt. Or on your GUI window, you say stop, so it will halt the processor. And then you type this command, mysim spun display statistics. So it will print a complete, recap of the number of hints, the number of branch instructions that were not taken, the number of branch instructions that were taken, the number of hints, the number of hits. So this is actually very good. There were so many hits for the hint instructions. Or branch hits. And there's another option that's available where you can provide the parameter hint. So SPUN will be, you can see when you hit Ctrl+C, you can see what SPU was used. It was 0 or 7 or 4. So you provide that as a parameter and you enter this command and you can get all the hint status data. And then you can see if you are really low level person, then you can see what is the usage of registers. The register reads, the register writes, and it gives a very good idea that if once you write your application, how many register reads and writes were done. And then there is an option on the simulator which prints the event log. In other words, when you try to print the event log, it will show you the summary over here in this little neat box. It will give you the number of cycles per instruction counts, right? DMA operations counts, how many gets were there, how many puts were there, how many translation faults were there on the PPE side. There is no address translation, remember, on the SPU. So that can only be for the PPU. How many fetch groups were issued, issue groups. This is a control panel where there is more data gets printed. And this is just a general execution. And then there is a visualizer summary display where you can get the number of DMA gets and puts, cycle instruction count, the channels, stalls, everything. And again, if you see, there is like all these 8 windows for 8 different SPUs. And when you do a pipe trace, this is how the output looks like. There is some more information available. You have the materials on your CD, but do try to go ahead and check this link out. It's on DeveloperWorks. There is a really neat paper written about how performance is extracted on the cell system simulator, some processes that are used, and it's a very user friendly. It's a small paper that that's very good beneficial information.